Hey guys, welcome back. It's Ben Neal here, graduate student from the Scripps Institution of Oceanography, and we're on board the research vessel Melville, as you see, in beautiful Southern California. It's a wonderful morning out here and we're getting ready to get back to science.
And I'm Jerry Reese from Data Middle School, and the goal today is to look at a particular type of science, in this case, coring.
Hey, I'm Steve Blatnick. I'm from Mid Park High School in Cleveland. Basically what our goal of today is to get down to the bottom of the floor of the ocean. And we are under about 1,500 feet of water. The difficult part is to get that mud up from the bottom, and that's where coring comes in. So the coring technique is going to get that mud up on board so the scientists can look at it.
Hi, I'm Jesse Vavrick. I'm a second-year grad student at Scripps Institution of Oceanography, and I'm interested in getting sediment cores from the Santa Barbara Basin to study the records of the geology here. My personal area of research is paleomagnetism, which is studying the recorded magnetism of the Earth's magnetic field. Paleo past magnetism. And anyway, so right over there is the rig which is collecting the samples that I'm interested in. It's what's called a piston coring rig, which is different than the rigs that went over the side yesterday, in that this rig collects a up to 20 meter long core, which could get us potentially back 12,000 years worth of sediment in those nice laminated annual varved layers. In this core, of course, there'll be several, they'll be the same top section as the casting core we saw the other day, but then continuous section further down. It's a little more involved. It's a gigantic rig, but with it we get a long continuous record broken up only by small turbidite sequences or underwater landslides from earthquakes triggered off the side of the channel. But those are useful for helping us date and correlate the different sections of the core so that we know when in time we are. Then we get back to the lab. When we split up the samples, we're going to be taking about 1-inch cubes into the side. Then these cubes are going to be tested for their magnetic properties. We're hoping that we're able to preserve the anoxic state at the bottom of the basin, so we're going to be very carefully sectioning, bagging, and storing in a refrigerator all the pieces of the piston core. Once we cut it open, though, we're hoping to see the same kind of varved sediments that you get in the cast-in and box cores. And we're hoping to see a much longer record. Long records have been taken from here before, but they're not as common because the logistics involved are a lot more difficult. However, we're hoping that we're going to be able to see a similar sort of material, but we're going to be able to tie it to older records of the sediment and thus actually be able to sample it, because previously long records have not had their anoxia preserved. So this will be new if we can get it.
To the west, where we don't have an anoxic bottom anymore, we should find a lot of interesting animals sitting on the surface, which is always fun to go and see the brittle stars and sea cucumbers and things like that. We're doing 4 types of coring, so we'll use this multi-core later on. That captures a very nice layer of the surface sediment, like the box core does. But in some respects it's a little easier to handle the tubes because they're small and they've already been pulled out of the sediment for you, as opposed to what Ben and I were doing of having to roll in the mud this morning. The box core is great because it captures this large surface area, and so you can take multiple samples out of it, and you can also get a large surface area if you're looking for things, say, on a particular, at the surface or a little bit below the surface. We're doing the cast-in core. That gives us a square cross-section, relatively long core, which will give us sort of the last, probably around 2,000 years or so of sedimentary record. And that's pretty cool. And because it's a square cross-section, we can slab it up into little slices that represent just a couple of years and get still a fairly large volume of sediment for picking through, looking for fossils.
Here we have the Makoma shell, which is 1840, which we had found in the bottom of the box core. And so we have the overlap between the upper box core and the lower casting core, and we go really far back in time now.
So that shell again?
1840, Makoma leptonoidea. It's a unique marker layer for a certain age.
Tomorrow we're going to be deploying the piston core, which is along the side of the ship, that gives us the longest record, the deepest time record that we can get, which in this case will be around 10,000 years. And the diameter is pretty big, okay? It's not quite as large around as the Caston core, but it's not bad. So we have these different dimensions of time that we're able to capture with these different devices.
My interest is in looking at the DNA that is concentrated from the dissolved DNA in seawater about 20,000-fold onto silicates in sand and mud and sediments. And so our main objective for my component of the study is to determine the quality of DNA that can be preserved back in time to the lowest sedimentary layers that we were able to collect in the piston core, which today happened to be a huge success, where we were able to achieve a core of approximately 18 meters in depth, which may actually allow us access back to sedimentary layers dating to 18,000 years ago. In a thimble full of sand, we have the DNA from millions of organisms in and about the sea.